So my first slide is just reminding you of what holds atoms together individually. And the first two things I bring up are metallic bonding and ionic bonding. The reason why I bring up those two to begin with is what holds one metal to another metal is the same that holds all of the metals together. That idea of delocalized electrons, that sea of electrons that are bouncing between the nuclei. Ionic, what holds one cation to another anion, is the same that holds all of the ions together. So we usually don't refer to either metallic bonding or ionic bonding with the term intermolecular force, because an intermolecular force is meant to be between two molecules. And metals and ionic compounds really aren't molecules. They're individual particles that are attracted to each other. So I believe last class I tried to make a note of that the term molecule is really reserved for things that are covalently bonded. However, recall last class, I'm not referring to covalent solids like a diamond that is covalently bonded to another carbon over and over and over again to make diamond. What we're going to refer to today for the most part is our covalent compounds that are either polar or nonpolar. But I just wanted to remind you of the intermolecular forces because covalent bonding is an intermolecular force, a sharing of electrons. My next slide is going to remind you of the difference between polar and nonpolar. Again, probably already know it, but I just want to make sure to emphasize the bonding that holds atoms together determines what holds the group of things together. So, and remember, polar covalence is an unequal sharing of electrons. Now, a polar covalent bond is due to a difference in electronegativity. Again, that's why I said between the bonded atoms. Hopefully, by now, you have seen enough instances of a molecule can be polar covalent as well without polar covalent bonds. That idea of symmetry, where is the molecule the same all the way around? Then it doesn't matter whether or not they're polar or nonpolar bonds. If it's symmetrical, it's nonpolar. If it's not symmetrical, very good chance it's going to be polar covalent. Things like pairs of electrons in a central atom usually throw off symmetry. Nonpolar, again, a nonpolar bond is an equal sharing of electrons because the atoms have similar electronegativities. But as I just mentioned, there's a difference between a nonpolar covalent bond and a nonpolar covalent molecule as a whole. Halfway done with this. And that idea of polar bond versus polar molecule is a pretty common thing to be brought up. And does it have dipole moments or not? Are there partial charges? Very common that you will see like a data table where it gives you the molecule and its melting point or its boiling point. And then you have to determine what type of bonding must it be. So my last three-ish slides are going to be a combination of me just going over the different types of intermolecular forces, and then I'd like to draw it out a little bit for you as well. So first off, all I have for this slide is an intermolecular force, which you'll usually see me abbreviate that IMF, which just like last class, by the way, that we were working a little ahead of schedule, we are working a little bit ahead of schedule today. So just like last class where you had 2 11 signs available, the one that was due today was the bond wrap-up. The one that's due next time is the lattice energy one. I did open up the intermolecular forces one as well, which would be due next week, Wednesday. So I'm sorry if there's confusion about which one is due when, but we are covering it today, so if you want to just get the work done, you can. Next week we will be doing a lab, so that's why I want to kind of get things out of the way if I can. Second bullet point was one that I tried to emphasize in Chem 1. The bond type within one molecule determines how multiple molecules are held together. So the intramolecular force determines the intermolecular force. Okay, we ready? So, sometimes these forces are referred to as van der Waals forces as well. What I'd like to do is give you all of my text for this slide, then I'm going to go over to Smart Notebook and draw out examples of these. So first off, dipole-dipole is between two polar molecules. So maybe if you write it out and you want to leave yourself a little space for when I draw an example. There's a specific type of dipole-dipole that is a little bit extra strong called hydrogen bonding. One that we did not talk about in Chem 1 was dipole-induced dipole. So we'll give you an example of that in a little bit, but one that we certainly talked about in reference to nonpolar molecules is dispersion forces, or London forces, or London dispersion forces. I've seen different texts call it different things. In Chem 1, we usually refer to it as London dispersion forces. That way we cover both main words. Then no matter who your source is, you're going to see it. I do say for dispersion forces, it's between nonpolar. However, dispersion forces exist between everything. The difference is, if you're polar covalent, your dipole-dipole or your hydrogen bonding is stronger than your dispersion force, so it's kind of secondary when it comes to what holds molecules together. As far as I'm aware, ionic compounds may even have dispersion forces. Individual elements. Because again, forces of attraction that hold things together as a solid, liquid, or gas, that doesn't just have to be a molecule. I believe last class you did a reading where it said helium can exist as a solid at negative 272 degrees Celsius, which is just 1 degree above absolute zero. Pretty close to that temperature is when helium's a liquid. Well, liquid helium, it's an individual atom, yet it's held together by dispersion forces. Why is it such a cold liquid? Because it's a tiny gas. So tiny things have to be moving really slow if all they have is dispersion forces holding them together. And liquid nitrogen is one that we commonly bring out as a demonstration where that's nowhere near negative 270 degrees Celsius, but it's still lower than negative 100 degrees Celsius, I believe. So it is really cold because it has to move slow, and that's kind of what this point is here. If you're a large particle or molecule, you have more dispersion forces than smaller ones. In Chem 1, I like to use the analogy of a hydrogen bond's like a thick rope holding two individuals together. It's hard to break that rope unless they're moving super fast in opposite directions. Dipole-dipole moments are a thinner rope. Dispersion force is like a little thread holding two things together. Pretty easy to break a thread between two objects if they're moving in opposite directions. But if you're a large particle, you could have a lot of dispersion forces, and you put enough threads together, it can make a rope. So there are some nonpolar things that are a solid or a liquid at room temperature because they're big. So again, I'm going to flip over and draw examples of this then to remind you of things that we covered kind of in Chem 1. A dipole-dipole, I'm going to use HCl as an example. Chlorine more electronegative than hydrogen. So the dipole-dipole is the attraction between the partial negative of one molecule and the partial positive of another molecule. It's very common that dotted lines will be used to show the intermolecular force. So this is our dipole-dipole. Some dipole-dipoles are stronger than others. It just is based upon how big the difference in electronegativity is between those bonded atoms. Remember where the term dipole-dipole comes from is polar molecules can not only be represented by these partial positives and negatives, they can also be represented by dipole moment arrows, which are basically pointing to the direction of electron density, high electron density. So that's where the term dipole-dipole comes from. It's the dipole of one molecule attracted to the opposite dipole of another. Within polar molecules, there are three special bonds due to having small atoms and big differences in electronegativity. These three, NH bonds, OH bonds, and FH bonds, are so polar that they create a special type of dipole-dipole called hydrogen bonding. And the best example we've used for that in the past is water. So that's the hydrogen bond. Now those first two examples are ones that we've gone over in Chem 1. The one that we really didn't go over in Chem 1 is dipole-induced dipole. I actually had an old AP student just write me recently. Now he's in college, so he was talking about taking college chemistry, and he had to explain to his roommate in college that when fish breathe oxygen, it's not that they are breaking apart the H2O bonds and taking the oxygen, that's what they're breathing in. This is what their roommate thought of how living creatures under the water breathe in oxygen, is they're decomposing water. But water has dissolved oxygen in it. And if you look at the fish tank in the library, it has the little waterfalls going in there. That's to help oxygenate the water. If I didn't have any sort of filter or any sort of way to move the water about, the water wouldn't be dissolving oxygen from the air, putting it in the water for the fish to breathe, and the fish would suffocate. Dipole-induced dipole is an example of that. Let's actually use a slightly different example of carbon dioxide. Carbon dioxide actually contains two polar covalent bonds. However, it's non-polar covalent overall because it's symmetrical. Carbon dioxide is dissolved in water as well. This is actually a very big issue. It's dealing with ocean acidification. The more CO2 that we pump into the air, the oceans are now grabbing that, just like my fish tank grabs some of the oxygen so the fish can breathe. It's grabbing that CO2, putting it in the water. That CO2 is lowering the pH, which, by the way, the term is ocean acidification, but the ocean is still above 7 on the pH scale. It is slightly basic. It's becoming less and less basic over time, though. So it's weird that they use the term acidification when it's not really an acid. But this is getting dissolved in water. The reason that can happen is when water is around the carbon dioxide, it can affect it. Think about the term dipole-induced dipole. Water has a dipole. It has a partial positive and a partial negative end. It's going to induce, it's going to make CO2 have a dipole. That's why the term is actually kind of nice, a dipole-induced dipole. What happens is if this is the partial negative end of water right here on the bottom one, these electrons right here, or in general, this part of the atom, any negativeness is going to get repelled from that because same charges repel. Now all of a sudden that negativeness is brought closer to this partial positive. We have created a dipole. We've created attraction. Another way to think about it. You might have friends that behave differently dependent upon who they are around. Does that seem like a reasonable statement? Let's take my favorite student, Joel, for example. Joel acts all intelligent and kind and caring in AP Chemistry because that's what my AP Chemistry students are. Intelligent, kind, caring individuals. When Joe is out on the football field, he's probably a little less kind and caring. Seem reasonable? Yeah. He's probably a little bit more smelly, sorry. But I've been in the locker room from football players and it stinks. Grauman, right? Yeah, he agrees with that as well. See, we got 2 football players in here that act, 3, sorry Helen, you're in the back. We got 3 football players in here that act differently depending upon who they are around. When carbon dioxide is around a polar molecule, a little bit of the water's polarness rubs off on it. It's kind of like, hey, you're around a person that's a good influence. I don't know if your parents ever say that. That friend is not a good influence on you. You should hang out with this person instead. Well, when carbon dioxide hangs out with water, it wants to be a little bit like water. Water affects it a little bit. It induces it to now have, get this electrons here away to make this somewhat a positive end, so there is some attraction. Now that isn't nearly as strong as the first 2 I went over up here of the dipole-dipole or the hydrogen bond, because those are always the way that it is. I mean, water always behaves the same way. So water is the one that can affect others. Nonpolar are the people that can be affected. The last force that was on that page is called the dispersion force, and dispersion forces is something that we did go over in Chem 1. Again, if I use carbon dioxide as an example, carbon dioxide is nonpolar. However, when I draw these electrons, even the bonded electrons, it isn't a stationary thing. Electrons are constantly moving around and orbiting. So at any given moment, these electrons could rotate up. These could rotate up. And for a split second then, I've created a small partial positive and a small partial negative that can attract each other. Dispersion forces are often called temporary dipoles because that rotation of electrons only lasts for a split second and then it goes away. So all of a sudden that dispersion force breaks, but a new one could form. And when you have really large particles, either large atoms or large molecules, they can have a lot of temporary dipoles. So even though 3 break in one instant, 3 more form, you could still be held together to be possibly a liquid, or even a solid if you have enough of them. Okay, there's one last term I have to bring up to wrap up notes then. And that term, I'll just keep it on this view here, is ion dipole forces. Ion dipole forces deals more with dissolving ionic compounds in water. What's that force of attraction? And we've gone over that before. So if you have water, it would be attracted to an Na+, and then the Cl- could be attracted to a neighboring water. That attraction in dissolving is referred to as ion dipole. It doesn't technically fall under the van der Waals force category because it's not two molecules. It's a molecule of water and then a particle, an ion, is something else. But we do consider it an intermolecular force between things. It's a pretty strong attraction, though, when you have a partial negative of water attracted to a full positive of sodium, a partial positive of hydrogen attracted to the full negative chloride. What you will see in the coming class periods, especially in the lab next week, is you can have a molecule that's enormous. And it can have polar ends, non-polar ends, even ions at the end of it as well. All of these play a role in how one thing can be attracted to another. Enough attraction and a less kinetic energy can make it a solid. Enough attraction but a little bit more kinetic energy can make it a liquid. And that's what the rest of our day is really going to be focused on, is those liquids.